Hi, kids. All right, we're gonna do a quick, fast review over this. This is gonna be over optics here. So let's do a real quick review over optics. So remember, two main parts of optics was reflection and then refraction. So what do you have to remember with reflection? Essentially, this picture. If I have a light coming in, this angle, which is my angle of incidence. Remember, you always measure your angle of incidence from the normal line. Remember, the normal line is perpendicular to the surface. It is going to bounce off, and that would be my angle of reflection, so that the law of reflection says this equals this, and that is always true. Remember that if you see something, light has to go to your eye. So if that is your eyeball right there, and I know that looks just like an eye, remember I did minor in art. Well, if you were, for example, looking at this person and the light bounced off a mirror that you had on the ground and went to your eye, your brain will think that that light traveled straight, and so you will see this upside down person here, like that. Okay, that would be a virtual image. Okay. Remember, real, virtual images you can see clearly. It's just that the light doesn't actually go there. Where a real image, the light does actually go there. Okay, but reflection. All right, we talked about curved mirrors. Remember, what is the key with curved mirrors? It is these two pictures. So if I have a concave mirror, see how it's caving in, and I have light coming in like this. And you guys saw the $1,000 demo to show this. That light will come together in a single point. That single point is called the focal point. Do you see how the light is really going there? That means that in your equation, when you're doing it, it would have a plus. The F would be plus because it is a real focal point, or in this case, from here to here would be your focal length. Remember also, if it's a spherical mirror, that F is at 1/2 the center of curvature. So like if I had a full mirror like this and the center was right here, F would be 1/2 of that. This distance to F is an important distance. Okay, that's one of the big pictures. The other big picture was, well, if I have a convex mirror, because you can see how it's vexing out, and if I have those same light rays coming in, where this mirror converges the light, brings the light together, this mirror is going to diverge the light. But again, it's not just going to randomly, reflect the light up. It's going to reflect it as if it came from a single point back here. And remember, if you were to draw your normal line, okay, that the angle of incidence has to equal the angle of reflection because it's the law of reflection, not the sometimes of reflection. But if you look here, well, that would be a negative F. Why? Because the light is not actually going there. That would be considered a virtual, okay, focal point. Okay, so if you're using your equation, which if you remember your equation, remember all your equations are on your formula sheet. Okay, for a convex mirror, the F would be negative. For a concave mirror, the F would be positive. But the key, honestly, is these two pictures. If you can remember these two pictures, you can draw your ray diagrams because you have to be able to draw ray diagrams as well. So if I just go through a quick example of what I mean. So let's say this is F, and let's say I have my object over here. Well, if you draw your rays, if I do this ray first, it goes parallel, and then it's going to go through the focal point. If I do that in reverse, it's going to go through the focal point. Now, you, of course, would use a straight edge. I'm just an amazing artist and I can draw things straight. But you, of course, would use a straight edge. And then there, and you can see, hey, look, that's where the image is going to appear. And then the third point, or the third ray is, there's my center of curvature, probably right about there. Well, that would go straight through. Or if you like, you could do the point that hits right here, where it would bounce and go to there. But then make sure you draw it in your image, and that would be a real image because the light really goes there, okay? You'll notice that the light is also upside down. Real images are typically upside down, not 100% of the time, but most of the time they're upside down. You can notice that it's smaller. To find that it's smaller, you could have also used the magnification formula. Again, this is on your formula sheet. Okay, but you're going to use that, and this is the height of the image, height of the object, the image distance, the object distance. So like in my picture here, that would be SO. That would be SI. And then remember, you guys did some labs where you graph stuff. So it's probably a good idea to look back at the labs and make sure that makes sense. But a lot of it just related back to this, okay? But again, I would recommend you look back at the labs. And then with this guy, if I wanted to draw the ray diagram for that one, it would look something like this. So let's say there's my F. And if I draw my rays, so okay, and then if I draw it towards this, I'm drawing it, it's going towards that far focal point, and then it's going to come out parallel. And you notice this ray and this ray are not going to meet, and that's okay. If you extend them back, they will meet. There's where your image is going to be. And then this time, let me do the other one. I could do the center ray, but I'm kind of running out of space. So I'll do the other one that should go to here. So it's going to be like, it's going to hit this part, and then it's going to bounce. I missed, but that's okay. That would be go to here. And then my teeny tiny virtual image would be right there, okay? So ray diagrams, the equation, mirrors, make sure that that makes sense. All right. Then we talked about refraction. So I got to go, let's talk about refraction. Okay. And the first thing we had was a picture that typically looked like this. Let's say n equals 1, n equals 1.33, so this would be air and this would be water. So first of all, let's talk about what that actually means. This is called the index of refraction, the index of refraction. Index of refraction is equal to the speed of light divided by the speed in the material. So we say air is typically saying now air, the index of refraction of air is actually like 1.001 or something. But we say if it's 1, that means the speed of light in a vacuum and the speed of light in the material are essentially the same. Light does slow down in air, just not very much, so that's why we typically call it 1. But this means that light is going to slow down 1.33 times. It's going to go that many times slower in water than it does a vacuum. But again, that formula is on your formula sheet, so you should have it. But if you have your picture, it would look something like this, okay? Where again, we measure from the normal line. So that this would be my angle of incidence. This would be my angle of refraction. We had an equation that showed you the relationship there, which was n1 sine theta 1 equals n2 sine theta 2. And again, this was Snell's law. And we did a lab with this where we graphed, sine and sine, and we looked at the slope. But again, the key is make sure you guys look back at the lab and make sense of the type of graph that you might see. but that would be your basic picture. Remember, in refraction, we also talked about something called the critical angle, so that if the light slows down, it bends down towards the normal. But if the light was going to speed up, it would bend. So let's say I'm going from glass to, I don't know, let's say water. Glass is 1.5, water is 1.33. So that light, instead of traveling straight, is going to bend this way, and it's going to speed up a little bit. Again, this would be my angle of incidence. That would be my angle of refraction. Well, if you were to increase the angle that it goes at, you could eventually reach a point where it goes right along the surface, so that angle is 90 degrees, so that my refracted angle would be 90. Well, this angle is called the critical angle. So you could set up Snell's law. It would be, in this case, it would be 1.5 sine of the critical angle equals 1.33 sine of 90, which of course is 1, and then you could solve for the critical angle. But again, understand what it is. Why is this angle critical? Well, if you go at an angle bigger than the critical angle, then you're going to get what's going to be called total internal reflection, where this angle is now equal to that angle, and the whole light ray bounces and stays inside. Fiber optics work on this principle. Diamonds sparkle because of this principle. Okay, Snell's law. Then we talked about lenses, so let's briefly go over lenses and make sure that that is okay. Lenses is essentially the same as mirrors. It's just that instead of bouncing, it's going to refract and go through. So if I draw my three important rays, here's my picture. Hey, look, my light is really going there. That would be a positive focal length for a convex lens, because the light bends together like this. And then my picture for the other one would look like this, where if I extend them back, I get a point here. That would be a negative focal point. And then I'll really fast go through the ray diagrams for each one, but it's going to be super duper similar to what we did before. It's just that the light is going through rather than bouncing off. So let's really quick go through that. So if I had so there would be my lens. Now, the reason we're going to do a focal point on both sides of the lens is the light could go left to right, or it could go right to left. So let's say I have my object here, and I'm going to draw my rays. There's my ray, the parallel ray coming in. So what is it going to do? Well, it's going to converge the light. So it's going to go like that. If I draw my focal ray, so it's essentially this one in reverse. So then I go through the focal point, and then it comes out parallel. I can already see where it's going to meet. But then if I draw my center ray, remember the center ray just keeps going straight. That it would look something like that. And of course they all met right there because I drew it perfectly. And that would be my real image. Again, the light is really going there. Okay, I would strongly recommend you practice drawing the ray diagrams a few times. You may want to practice the one that is a virtual image as well. So if I was here, you know, if we drew our rays really fast. Now just be careful with this one, guys. This focal point, the object, and then lens, it just so happened that my lens, it touching the top. Like, if my lens was bigger, that ray would be exactly the same. You guys with me there, okay? If my lens was smaller, that ray would be the same. Okay, these are just rays that we use to try to figure out where it's going to be. And then if you drew your center one, it would look like this. Hey, look, they don't meet over here. That's because you have to extend them back. Oh, they meet right there. There's my virtual image. Okay. All right, I'm going to do one for the concave. All right, so let's do it real fast. All right, ready? Parallel ray. Like it's coming from there because it's going to bend up. And then this one I have to go towards the other one. So I'm going to go towards the, I'm going towards the focal point on the other side, and then it comes out parallel. And then if I drew my center ray, these rays are not going to meet over here, but if I extend them all back, they meet right there. There's my virtual image. Okay, just remember, you would be using the equation, look back at the labs, make sure you guys understand that. But that is Unit 1 super duper de-duper fast, just as a quick overview. If you have other questions, then go back into the unit and use those more detailed review videos. But yeah, Unit 1. Bye, kids!